Putting together this Big Winter School. So I'm going to talk first about some questions on counting, number field. So first I'm just going to be asking some questions, and you already got a taste of a couple of these kinds of questions in Jordan's talk. So first of all, I'll just mention that we know classically, given x greater than 0, there are finitely many number fields. Okay, so either up to isomorphism or in Q bar with discriminant at most x in absolute value. So it's been natural to ask, how many are there? So what are the asymptotics in x of, I'm going to call it n of x. So slightly unfortunately, my big X is playing a role like Jordan's big N. I'm going to use N to count these number fields. So, which is the number less than X. So what are the asymptotics of this counting function that counts the number fields of discriminant up to X? It turns out that to approach this problem, it's slightly more tractable if we don't just ask about all number fields, but we filter them by some of their invariants. So the first invariant I'm going to talk about is their Galois group, and so if K is a number field, degree n, I'm going to call the Galois group of K which I'll write as Gal K to the image of Gal K tilde. This will be the Galois closure. Okay. So first of all, by what's now become a pretty standard abuse of terminology, I'm going to be talking about the Galois group of K, even when K is not Galois. So that's the first thing to be aware of. I'm going to use this Gal K to mean the Galois group of any number field. And what group is that? Well, first of all, it has to do with the Galois group of the Galois closure. So this K tilde here is the Galois closure of K, so something that should have a Galois group in the traditional sense. And then that Galois group of the Galois closure, it has a permutation representation, or a map to the symmetric group, given by the action on the N homomorphisms K Q bar. Right? So I'm going to just unpack that a minute. Think about an example, sort of, if we write K, let's say Q adjoin theta, and then theta 1 and theta n are the n conjugates of theta in Q bar, then this the action of the Galois closure of K, which will include all those conjugates over Q on just these conjugates, because of course the maps from K into Q bar are simply the maps that take theta to each of these conjugates. And so this is more than a group. It's not just abstractly a group, it's a permutation group. So this gal K, when it's not just I said it's the image, and so it's the image here in Sn, so that's not just a group, but it's a group with an action on n things. So gal K is a permutation group. And that's part of its structure. Two permutation groups are isomorphic if they're isomorphic as groups, and their action on n things is the same up to relabeling of those n things, or that's conjugation in Sn. Okay, so now that's just a notion of Galois groups. So for example, here's an example we'll see. An example, so if K is a cubic field, right, so then its Galois group is a subgroup of S3. It has an action on 3 things. So if K is what we call a cyclic cubic field, so actually, K is Galois, and this gal K is A3 or Z mod 3. It's a cyclic group of 3 elements. But if K is non-Galois, so non-Galois cubic field, then this Galois group is S3. And both when I write A3 and S3, I think from that it's clear how I mean them to act on 3 things. Later we'll have maybe some of these groups acting on different numbers of things. Okay. So with this notion of Galois group, I can ask not just how many number fields are there up to discriminant x, but how many are there, say, of a particular Galois group. So what are the asymptotics of, say, n gamma of x, which I define to be the number of K with discriminant most x, and Galois of K to be isomorphic to some permutation group. So since these questions are hard to answer, I'll just keep asking more of them. That's sort of the general strategy. Another way that I can ask an even finer question is by not just restricting the Galois group, but also restricting local behavior. So local behavior. So given place P of Q, and I write P, but since I said place, I really do mean, so a prime or infinity. We can form, say, KP So this is what a K looks like at the prime or place P. And I define that by changing the scalars from Q up to QP. So by Q infinity, R, completion at the infinite place. So this is just slightly more than the local data we're used to thinking of. Normally, when we have a number field K, and we have a prime P of Q, we're used to thinking of how that prime splits in K, say, P1 to E1, ER to the ER, so that prime splits in the ring of integers of K in some way. And this KP, it captures that information and a little bit, just a little bit more. So, in particular, So KP is direct sum of field extensions QP. More precisely, KP is the sum of the KPIs. So these are the completions of K at the places repeat. And so this direct sum of field extensions, QP, another way to say that is tau QP algebra. So if you don't already have to know what a tau QP algebra means, you can just take it to mean this, and if you already were taking it to mean something else, then I'm just telling you that it's the same as it's equivalent to this. So this KP, it captures the splitting and the inertia and the ramification type of K and P, and just slightly richer data than that. So we did ask, what are the asymptotics of, let's say, now I'm going to have some local data as well as a Galois group. So let's say count number fields, discriminant, most X, Galois is gamma, let's say K, P, isomorphic to some fixed M, QP, a tau QP algebra. So that's now a question where I'm counting number fields with some particular Galois structure and some particular local behavior. So, for example, so here's a very concrete classical example. So how many quadratic number fields are there split completely at 7? So that question asymptotically in X, that's this question for gamma is S2, so the permutation group S2 acting in its normal way on two things. And M here is, so split completely at 7. would mean that the eta algebra is just the direct sum of Q7 with itself. Now, I also want to use the language of probabilities, just like Jordan was using in his talk, to think about questions like this. So how many quadratic number fields are there split completely at 7? Well, if I knew how many quadratic number fields there were, then maybe even if I didn't, like I could ask what proportion of the quadratic number fields are split completely at 7. So I'll use the language of probability, and let's just say, so I will give it just in this, I will define this language by example. So say that P for probability, that's bad. Should I color in my P? Okay, this P for probability. So if I say, like, what's the probability that quadratic K is split completely at 7, I'm writing that subdiscriminant to remind me that the thing that I'm taking randomly is K, and I'm taking it by its discriminant, so this is the limit as x goes to infinity. So it's going to be the proportion of K of discriminant of K less than x, Galois K, S2. Of these, I'm going to count just how many are split completely. Galois K S2, K split completely at 7. I'm just going to count up to discriminant x what proportion of those are split completely at 7, and then I will take up to discriminant x, and then I'll take the limit at x. So one natural question that comes out of thinking of this as a probability is the question of independence. So our probabilities different primes independent. So now that I've outlined some of the big questions that we might ask, I want to think a little bit about these questions and compare them to something that's more classical. So when I say here the probability that a quadratic K splits completely at 7, that sounds an awful lot like something more familiar, the Chebyshov density theorem, which tells us something about the probability that primes split completely in quadratic extensions, right? It sounds awfully similar, but in this question here, we have a fixed 7, a fixed prime 7 here, and we're taking a random K, whereas when we use the Chebyshov density theorem, we fix some field, and then we take a random prime and ask about the probability that it has some behavior. So I'm going to make maybe I will slightly where I want to keep that question up. I'm going to make a big chart. So we can imagine that we can make a big chart, and along one axis, I'm going to list the primes. And along the other axis, I'm going to list the quadratic fields. I hope I determine it, but you can just imagine if I'm off a little bit. Okay, so here's my list of primes and my list of quadratic extensions. And for each quadratic extension and prime, I have a question. Does this prime, it could either split, or it could be inert, or it could ramify. So it could either split, or be inert, or ramify. And so for each quadratic extension and each prime, I could just make a chart. What does it do? All right, so this is a nice exercise in a first course in algebraic number theory, which I hope I didn't make too many mistakes. I tried to do some of these here. Okay, so you just go along and everything is split, inert, or ramified, and you can keep track of those statistics. And there's so many places I could have made mistakes originally or copying it from my paper. So, but whatever. They're just some answer for any particular prime and number field. And the Chebyshev density theorem, or in this case, more simply, something like Dirichlet's theorem, primes and arithmetic progressions and quadratic reciprocity, tell us that if we look in a row, so if we look in a row, if we look far enough out, we get about 1/2 S's and 1/2 I's, and sort of 0 R's. That's this proportion. So we do get some R's. We see here a bunch of the R's, right? But if we look out 0% asymptotically, we get, maybe I should say, we get asymptotically 1/2 S's, 1/2 I's, and 0 R's. And so this question here about the probability that a random quadratic field splits completely at 7, it's saying instead of looking in a row, in a single row very far, what if I look in a column? I take one column and go up, up, up. So already something that's different when I go up in a column actually is that in the column I get R, I get ramification with positive probability. So already it looks a little different than the Chebyshev density theorem. So I'll actually just tell you, say 7 was the one we were asking about originally. So the probability that K quadratic splits at 7 is 7/16. So if I look up in one of those columns, if I go far enough up, about 7/16 of the time, I'll get an S for splits, and the probability that I get an I, that it's inert at 7, is 7/16, and the probability that I get ramification, I told you now, unlike the Chebyshev question, unlike the horizontal question, the vertical question has a positive probability for ramification, and here it's whatever's left, 1/8. It's not actually, never mind. So the answers to these questions are, as you can see, different, but they're not entirely unrelated. We might like the fact that at least if we, Okay, once I tell you that there's a positive probability of ramification at a fixed prime in a random quadratic field, you already know it's not going to look like Chebotarev, but at least if I restrict it to the unramified at 7 fields, at least I get the same ratio of probability. So if I condition on being unramified at 7, in this vertical question, I would at least get the same answer as the horizontal question. So these numbers, for example, here they're basically exercises in my notes, and after Jordan's talk, and it sounds like we're going to be doing a lot of counting square free integers, I would hope that all of you would be very good at working these out for yourselves after this school. So now, what about looking at this chart? So what does this question of independence say in this chart? So let's maybe first think about sort of Chebotarev independence. I.e. the independence of fields or rows in our chart. So that would say if I take the question of Chebotarev independence, so if I take two rows, let's just say I take the bottom 2 rows, basically I know that I see half the time I see an S, and half the time I see an R. So if I look in 2 rows, independence would be if I saw, sorry, half the time I see an S and half the time I see an I. Independence would be if I see SS, SI, IS, and I. In 2 rows, if I see each of these 1/4 of the time, that would be asymptotic independence. And in fact, this is true. If you take 2 rows, in fact, if you take, well, actually, okay, so if you can take any 2 different rows, you do have this this independence. And we can even say more generally, if I don't just have quadratic number fields, but say I listed all my number fields here, for simplicity, there's so many things I'm going to look at all at once. Okay. All right. I really like this chart, so we're going to keep looking at the chart. So, okay, if I listed all, and for simplicity, maybe I'll list all Galois number fields, for my rows. Here I just was listing quadratic, but if I listed all of them, in fact, we have that there is dependence. So Chebotarev, or dependence in the rows, dependence, if and only if 2 fields, say K1 and K2, have a subfield in common larger than Q. So that's why we don't get any dependence in the quadratic fields, because if you have 2 distinct quadratic fields, they don't have some subfield in common. And once you think about this, it certainly intuitively it's not so surprising that this should cause some dependence. If I'm asking about primes, splitting in 2 different fields and they have some big common subfield, the splitting in that big common subfield affects the splitting in each of the fields, and so there just couldn't, intuitively it would have to be dependence, and this is in fact result that I get, this is actually another exercise in the notes, to see that you always get this dependence. So the story is pretty clean when you're asking about these kind of rows. And so, for example, even if we went back to here and we asked about, say, 3 different quadratic fields, then the question would have to do with, well, you know, when you composite, say, 2 of those quadratic fields, is that 3rd quadratic field sitting in there? If so, then there's going to be some dependence, and otherwise there's not. And so there's a pretty succinct story to the question of is there dependence or independence of fields? It's basically, well, do they contain each other, or do they contain some common thing? And so a much trickier question is, what do we even expect for primes? And so if I look in the column corresponding to the prime 2 and the column corresponding to the prime 3, do those S's and I's and R's there, do they look independent? Are they dependent? Does that answer in some way depend on my choice of 2 and 3? I think it's not so clear what to even guess, except perhaps some kind of Occam's razor guess that they should all be independent, because I can't think of any reason why they would be otherwise. But that's where we get a lot of our best conjectures, so that kind of philosophy. All right, so we will come back many times in these talks to these questions. So for now, and we will even answer some of them, especially in the quadratic case. But before we get to any answers, I want to ask more questions. So those were my questions about counting number fields. And now I want to ask some questions about counting class groups. Already we saw examples of this as well in Jordan's talk. So here, I'll maybe just start with a more sort of precise question. So here, I'm going to think about counting class groups of imaginary quadratic fields. So here, even the right question to ask gets more complicated if you ask it for other kinds of fields. It's only slightly more complicated for real quadratic fields. But if you wanted to, say, ask a question about class groups of fields with some Galois structure gamma, even the right question gets more complicated. So as opposed to the counting number field side, where I could basically ask all the questions in the same language, here for simplicity, I'm going to restrict to only the case of imaginary quadratic fields, even to ask my question. So here's a question, which is given an odd prime P and finite P group G. But portion imaginary quadratic. Okay, so I'm going to maybe stop writing it now that we've written it. So when I ask this, I'll say here ordered by discriminant. So that always means that I'm going up to discriminant taking the discriminant up to x, looking at the proportion up to that, and then taking the limit of the proportions, like we've done over and over. So what proportion of imaginary quadratic k have the COP subgroup of the class group K isomorphic G. Okay, so I've got an imaginary quadratic field K. It has some class group, which we know is a finite abelian group, which we often describe as measuring the failure of unique factorization in the ring of integers. Okay, so some finite abelian group. We know what all finite abelian groups look like. They're just the direct sum of their COP subgroups for each P. They have a P part for each P. And so I'm asking about, you know, say for any prime 3, 5, 7, what is, what on average does the P part of the class group look like? In particular, how often is it each of the various possibilities? So I restrict here to the odd primes because genus theory tells us something about the P equals 2 case. You can actually by taking twice the class group, you can get rid of what genus theory tells us about. I do that in the notes. You can look there and to the references there for more details. But for now, in these talks, I just won't worry about P equals 2. So that's why I didn't ask for P equals 2 because I already know something. And the point of this question is that we know almost nothing about the answer. So besides just asking, so how often is, say, the CLO3 of the class group, how often is it how often is it trivial? How often is it Z mod 3? How often is it Z mod 9, Z mod 3 cross Z mod 3? Each of the different possibilities for a 3 group, how often is the CLP of the class group that? And so we can also ask for averages of other F over class groups. So that question is about the average value of some function F, where F is the characteristic function of my group. So the above is asking about that, where F is just the characteristic function of, are you indeed my group G? But maybe another example is if we ask, you know, what is the limit K imaginary quad discriminant less than X, and over these K, so I'll put this little arrow pointing, I'm summing over those Ks. That arrow was pointing to all those things that I would have written under the summation sign if I'd had a chance. What if I average the size of, say, the class group of K mod P? Okay, so what's the average size? So this question is, what is the limit, if it exists? Maybe it doesn't exist. What is the limit, if it exists, of the average size of the P part of the class group of a quadratic field? So instead of just asking for the average size of that thing, I could ask for the K. That's like the first moment I could ask about the K moment. Maybe I should. That was going to be a little K. I can make a piece of little K. Okay, so I could ask about the K moment. So that's another function. I could ask how it averages. And here's another example, which is going to come up again in my talks, and I bet will make an appearance somewhere in Jordan's talk. Is we could ask for the function. Okay, so the same denominator, same summing over K's, but now I'm going to count the number of surjections from the class group of K to A. So A, some fixed abelian group. And I could ask, that's another function of groups that I could average over class groups. How many surjections does it have to A? And so there's an exercise in the notes about, say, relating these for some examples. So this question is actually related to this question, just by some finite abelian group theory. So for a function f on finite abelian groups, I'll write in field f for this average. So the average of f, which is a limit which is not even clear that it exists. I mean, not just not clear, but in general we don't know. It's an open question if it exists, but if such a limit exists, averaging the values of f over class groups of imaginary quadratic number fields ordered by discriminant, I'll write it in field of f, and that's, I think, the field average f. So in this case, I am going to jump now to some conjectures for what the answers to these questions are. So for the first questions, the counting number fields question, even though they're a little more basic in some sense, to even state the conjectures is going to take some work and background to even make sense of them. But in this case, especially because I've simplified by just thinking about imaginary quadratic fields and their class groups, I can state here the Cohen-Lindster heuristics. Which are conjectural answers to all of these questions about class group averages, about these field averages of f for various f, like the characteristic function or the K power of the size of the p part or whatever. Okay, so the Cohen-Lindster heuristics, okay, so they start from the following observation, which is that things occur in nature with frequency inversely proportional to their number of automorphisms. So in the notes, there are actually several examples of this phenomenon that you can work out for yourself. This is a really, this observation is something that is true in many, many cases of mathematics that you can prove. And I will just give you one tiny example that picks up on a theme that we've already talked about, which is if we look at cubic fields in Q bar, okay? So for cubic fields in Q bar, so the Galois ones, Galois appear once and have 3 odds. And the non-Galois, they appear 3 times. There's 3 conjugate fields if you're non-Galois, and they have 1 odd, just the trivial automorphism. Okay. So there's my one example of this very robust phenomena. And I encourage you to think about many more examples, such as the ones in the notes. And so the Cohen-Lindster heuristics say, well, if we don't know anything about the odd part of the class group, let's just imagine they just appear inversely proportional to the size of their automorphism groups, because that just often happens in in nature. So here's a conjecture, which is due to Cohen and Lenstra, and then stated in a way that Cohen and Lenstra for the odd part, and then extended by Girth for the even part. So it says for any reasonable f, we have at, okay, well, so in order for it to work for people to, I should say, this is taken over not the class group, but twice the class group. Right, that's slightly different from what I wrote above. But let's not worry about that. So that this should be the average over groups of the function. Right, so this is groups, finite abelian groups up to size n of, so if we count those groups by 1 over their number of automorphisms, and so here we also finite abelian groups size the most n, and then we average the function over groups, but weighted by their number of automorphisms. So we take groups up to size n, each weighted by their number of automorphisms, and that tells us how to sensibly average our function. We're not going to average our function just by taking its average value on a bunch of groups, because that discounts the fact that groups really don't appear equally often. They should appear inversely proportional to the size of their automorphism group. So I'll call this the group average of f. So Cohen and Lenstra conjectured that for lots of functions f, and they're not actually so precise about what reasonable should mean, but they give some examples. For example, an f that depends on the CeLO-P subgroups for only finitely many p, or also they like f is the characteristic function of cyclic groups. For any reasonable f, whatever that means, we think that the field average of f, so taken over the class group of imaginary quadratic fields, should be the same as the group average, where things are averaged over groups that are weighted by 1 over their number of automorphisms. And so Cohen and Lenstra compute M group of f for many examples of f's. So that's a problem in not arithmetic statistics, but group theory statistics. It's actually not trivial, but it is just a question about finite abelian groups, so it's certainly much more tractable than a question about class groups, but it still takes them some work, and they compute M group of f for many, so for many different f's, and so then one has actually a precise conjecture for M field of f, what you think. So I'll just maybe give 2 examples. Okay, so example, if f is the indicator function of the odd part of the group is cyclic, then M group of f, they compute, is around 9.77575. So they think that almost 98% of imaginary quadratic fields should have the odd part of their class group cyclic due to their conjecture. So another example, which Cohen and Lenstra compute implicitly, though they don't really highlight, but will play important role, I think, in some of our talks is that if A is a finite abelian group and F is the number of surjections from G to A, so that was an example we had before, then M group of F is 1. So that the group average of that F is 1. That didn't depend on A. So that's a very nice kind of function to average over your finite abelian groups, and therefore probably over your class groups. And we will see it again later.